Hello friends, welcome back to ASMR Nerd Herd. Thank you for joining me this evening. Why don't you find a comfortable spot, somewhere you can feel completely safe and at ease. Just let your mind grow quiet and your body grow heavy. And allow my voice to be a gentle guide. Tonight we are going to drift far, far away from our everyday world and journey together into the deep, deep, quiet cosmos. We're going to travel to the very edge of what we know as I slowly and calmly talk about one of the universe's greatest and most beautiful mysteries, black holes. There's nothing to be afraid of here, only wonder. So relax, close your eyes if you'd like, and let's begin in tonight's episode of Sleep for Science. Before a black hole can be born, a star has to live a spectacular life. And before that, there's just space. Imagine a vast, dark, and utterly silent expanse. A space between the stars. It looks empty, doesn't it? But it isn't. It's actually filled with a fine, delicate mist. A cosmic cloud of gas, which we call a nebula. Think of it as a nursery for stars, a celestial cradle just rocking gently into the arms of the galaxy. These clouds are immense, spanning light years across. They're these beautiful, ethereal tapestries woven from hydrogen, the universe's most basic building block, with a little sprinkle of helium. It's made of these tiny grains of carbon and silicate as well. The ashes of the long-dead stars scattered across the cosmos, just waiting to be reborn. Within this grand, cold cloud, some regions are just a little bit denser than others. A little pocket where the gas is a bit thicker, a bit more gathered, and here, gravity, the quiet, persistent force of the universe, starts to work its magic. It's a very, very slow process. Imagine a single dust particle gently attracting another, and then another. It's a cosmic dance of attraction, so slow it's almost impossible to perceive, taking millions of years. As more and more gas and dust gather, these little pocket of the nebula begin to pull in on itself. The gravitational pull gets stronger as it pulls more matter inward. Its pull grows stronger still. It's a gentle feedback loop of creation. And this growing clump of matter, the baby star, is called a protostar. As the cloud collapses, the pressure at its center starts to build. The gas particles, once so far apart, are now crowded together, bumping and jostling. This crowding causes the core to heat up, glowing with a dull red light. A faint warmth in the cloud heart of the nebula. For thousands upon thousands of years, this protostar keeps gathering mass from its parent cloud, growing larger and It's like a cosmic ember slowly being fanned into a brilliant flame. Eventually, after an immense amount of time, the pressure and the temperature at the core of the protostar reaches a critical point. A point of ignition. The hydrogen atoms squeeze together with truly unimaginable force begin to fuse. They merge to become helium, and this process, nuclear fusion, releases a tremendous amount of energy. This energy pushes outward from the core, a powerful radiant pressure that fights back against the inward crush of gravity. When these two forces, the outward push of fusion and the inward pull of gravity, reach a perfect, delicate balance, a star is born, a stable, shining star taking its place in the grand tapestry of the night sky. Our journey tonight, though, isn't about any star. We're following the path of a true cosmic giant, a massive star, born from a particularly large and dense part of the nebula. A star destined for a very different and much more dramatic fate. Let's imagine one such star, a brilliant blue giant, at least 20 more times massive than our own sun. Its life will be bright, beautiful, and incredibly short. Our massive star shines with a fierce blue-white intensity. It's a behemoth, a king among stars. Its immense mass means its gravity is strong. So, to counteract the crushing force, the furnace in the core has to burn with an unimaginable force. While a smaller star like our sun sips its hydrogen fuel, lasting for billions of years, our giant star gulps it down. It lives its life in the fast lane of the cosmos. Its core is cauldron of creation, where the intense pressure and heat allow for the fusion process that smaller stars can only dream of. At first, like all stars, it fuses hydrogen into helium. This is its main sequence, the longest and most stable phase of its life. For millions of years it hangs in the blackness of space, a beacon of brilliant light, pouring out its energy into the void. But because it burns so hot and so fast, its supply of hydrogen in the core eventually starts to run low, and this is where the star's life gets really interesting. The outward push from hydrogen fusion weakens, and gravity starts to win the battle again. The core contracts and heats up even more. This new higher temperature is hot enough to ignite the helium that was created before. The star begins to fuse helium into carbon. It's found a new source of fuel, a new lease on life. The new fusion process releases even more energy, causing the star's outer layers to expand dramatically. The star swells into a red supergiant. Its surface cools, giving it that reddish hue, but its overall size is now astronomical, so large that if you place it in the center of our solar system, it might swallow the orbit of Jupiter. Inside the core of this red supergiant, a fascinating process is unfolding. The star has become a kind of cosmic onion, a series of concentric shells, each one fusing a different element. As the helium in the core is used up, the core contracts when the last stage begins to fuse into heavier elements like neon and oxygen. When the carbon is gone, the core contracts again, gets hotter even still, and starts fusing neon into magnesium, then oxygen into silicon. And finally, in the last frantic days of its life, it fuses silicon into iron. Each stage of this fusion happens faster and faster. The hydrogen burning phase lasted for millions of years. Helium burning, a few 100,000. The carbon phase lasted a few hundred years. That final silicon burning phase might last for only a single day. The star has built up a core of iron, and with iron, the journey of creation just stops. Iron is the ultimate ash. Fusing iron atoms doesn't release energy, it actually consumes it. There is no more fuel for the star to burn. The furnace at its heart has gone out. For millions of years, the star has been held in a delicate balance. The outward radiation pressure from fusion perfectly countering the relentless inward crush of its own immense gravity. Now, in an instant, that outward pressure is gone. Gravity is unopposed as it takes over with catastrophic speed. In the final moments of the star's life, there's an eerie quiet before the storm. The iron core, no longer supported by the fires of the fusion, it has nothing holding up. In less than a second, a fraction of a second, the core collapses. Can you just imagine a structure the size of planet Earth, containing the mass of 1.5 suns, suddenly imploding? The collapse is so rapid and violent it triggers a cascade of events. The outer layers of the star, which were once peacefully floating in space, now have nothing supporting them. They begin to fall inward, racing towards the collapsing core at a quarter of the speed of light. As the core collapses, the iron atoms are squeezed together with a force that's hard to even comprehend. The electrons and the protons in the iron are forced to merge, creating a sea of neutrons. The core becomes a dense, rigid ball of neutrons, a proto-neutron star. This whole collapse from an iron core to a ball of neutrons takes only a moment. When the infalling outer layers of the star slam into this newly formed, incredibly hard neutron core, they rebound. This rebound creates a shockwave of monumental proportions. The shockwave blasts outward, tearing through the infalling layers of the star from the inside out. And this is what we call the supernova. The star, which lived millions of years, dies in a single, breathtaking, violently explosion. For a brief period, this one explosion can outshine an entire galaxy of billions of stars. It's one of the most energetic events in the entire universe. The explosion flings the outer layers of the star out into space at incredible speeds. The beautiful shells of elements that the star so carefully forged, the oxygen we breathe, the carbon in our bodies, the silicon in the rocks beneath our feet are scattered across the cosmos. This stardust will one day form new clouds, new planets, and maybe new life. The star, in its death, seeds the universe with the building blocks of everything we know. But our story doesn't end with that beautiful dust. Our focus is on what's left behind, the fate of that collapsed core. For a slightly smaller massive star, the core would remain as that neutron star we mentioned, a tiny, incredible dense object. But our star was a true giant, remember? It was more than 20 times the mass of our sun. And so the leftover core, even after the supernova explosion, is still too massive. The force of gravity is simply too overwhelming. Even the incredible rigidity of neutron star can't withstand the crush. The collapse continues. The remnant core keeps collapsing under its own weight. There is no force known to physics that can stop it now. The neutrons themselves are squeezed out of the existence. The very fabric of space and time is put under an unbearable strain. The core collapses and collapses and collapses until all of its mass, the mass of several suns, is crushed into a point of zero volume and infinite density. This point is called singularity. The heart of the star has been squeezed into a region smaller than an atom, smaller than anything. It has in effect punched a hole in the fabric of space-time itself. A black hole is born. It isn't an empty hole, though. It's a region of space that contains an enormous amount of mass, packed into an infinitely small point. Its gravitational pull is so immense, so powerful, that nothing can escape it. Not a planet, not a star, not even light itself. The name black hole is just so perfect, because that's what it is, a hole in the observable universe. Any light that falls into it is lost forever. Any light that passes too close is captured. It doesn't shine, it doesn't reflect, it doesn't emit anything. It's a region of perfect blackness, a silhouette against the backdrop of the stars. The birth of a black hole is both an end and a beginning. It's the end of a magnificent star's life, and the beginning of one of the most enigmatic and fascinating objects in all of creation. It sits there now, where a brilliant blue star once shined, silent, waiting, warping the space around it, bending the light that dares to pass by, and slowing the very passage of time. Let's take a gentle journey closer to this brand new black hole, where we'll be extra careful. We won't get too close, but we'll try to understand its strange and wonderful properties. As we approach the black hole, the first thing we might notice isn't the blackness itself, but the light around it. You see, the black hole's gravity is so strong that it acts like a lens, bending the path of light from stars and galaxies far behind it. This effect, which we call gravitational lensing, creates a beautiful distorted halo of light, a shimmering ring around a perfect circle of darkness. This glowing ring isn't from the black hole itself, but it's the light of the universe being warped and twisted by its presence. It's a visual signature of the immense gravity we're approaching. Now, let's talk about the most famous feature of a black hole, the event horizon. The event horizon isn't a physical surface. You can't stand on it or touch it. It's an invisible boundary, a point of no return. It's the precise distance from the singularity where the gravitational pull becomes so strong that the escape velocity, the speed that you need to pull away, is greater than the speed of light. And since nothing in the universe can travel faster than light, anything that crosses the event horizon is trapped forever. A spaceship, a planet, a beam of light, once it passes this invisible line, its journey has only one possible destination, the singularity at its center. Let's imagine you're watching a brave astronaut in a powerful spaceship, cautiously approaching the event horizon. From your safe distance, you'd witness something very, very strange. As your friend gets closer and closer to the horizon, clock relative to your clock would seem to slow down. This is something we call gravitational time dilation. The stronger the gravity, the slower time passes. As your friend's ship inches towards the horizon, you would see it appear to move slower and slower and slower. Its light would become redder and dimmer. Eventually, as it reached this horizon itself, it would appear to freeze completely. From your perspective, your friend would be frozen in time, at the edge of the black hole for eternity, just fading away into nothingness. But for the astronaut, their experience would be completely different. From their perspective, their clock is ticking normally. They don't feel any slowing of time at all. They would simply drift across the event horizon without any bump or jolt, like crossing an invisible line in space. But once they cross it, they see the universe behind them warp and distort. While ahead of them, there is only darkness and the inevitable pull towards the center. There's no turning back. All possible paths now lead only to the singularity. It's helpful to remember a common misconception here. Illustrations often show black holes as funnel-shaped, like a drain in a 2D. This is just to help us visualize how gravity wells work. In reality, a black hole is spherical. The event horizon forms a perfect sphere around the central singularity, so it's not a funnel you fall down, but a dark spherical prison you drift into. Now, let's talk about one of the most famous and maybe most terrifying ideas associated with black holes. A process with a wonderfully descriptive, if slightly horrifying name: spaghettification. This is what happens to an object or a person as they get very close to the singularity, especially with a smaller stellar mass black hole. The effect is caused by a tidal force and extreme gravitational gradient. Imagine our astronaut friend again after they've crossed the event horizon. They are now falling towards the singularity. The gravitational pull of the black hole isn't uniform. The part of their body that's closer to the singularity, let's say their feet, is being pulled much more strongly than the part of the body that's further away, their head. This difference in gravitational pull would create an immense stretching force. Their body would be pulled apart, elongated, stretched lengthwise. At the same time, the gravity on their sides would be squeezing them inward, compressing them from all different directions. The result: they would be stretched and squeezed into a long, thin stream of atoms, just like a piece of spaghetti. This is spaghettification. It's the process of being totally ripped apart by the most extreme gravity unimaginable. We have actually observed this happen to stars that wander close to a black hole in what are called tidal disruption events, where the star is shredded at its most material form, a glowing disk, before being consumed. The intensity of spaghettification depends on the size of the black hole. For a smaller stellar mass black hole, like the one born from our giant star, the tidal forces at the event horizon are immense. You would be spaghettified before you even cross to the point of no return. However, for a supermassive black hole, which can be millions or even billions of times the mass of the sun, that story is different. These giants are so large that their event horizon are much further out from the singularity. The gravitational gradient at the horizon is actually much gentler. An astronaut could cross the event horizon of a supermassive black hole without feeling any immediate tidal forces. They would be safely inside the black hole for a little while. The spaghettification would still happen, of course, but it would occur much later as they got much closer to the singularity at the center. So while the name is a little bit playful, the process it describes is a powerful demonstration of how gravity behaves in its most extreme form. It's the ultimate destruction, breaking down matter in its fundamental components. We touched upon the strange effects of a time near a black hole, but let's drift into this concept a little more deeply. It is one of the most mind-bending consequences of Einstein's theory of general relativity, the theory that tells us that gravity isn't a force in the way we usually think of it, but a curvature, a warping of the very fabric of space-time itself, and massive objects like black holes warp space-time dramatically. Okay, so imagine space-time as stretched out rubber sheet. A small object like a planet creates a small dimple. A star makes a deeper one. A black hole creates a well of seemingly infinite depth. Time is a dimension of space-time, and so it's also affected by this curvature. The deeper you go into a gravity well, the slower time flows relative to someone in a weaker gravitational field. Let's go back to our two clocks. One clock is here on Earth, far from an extreme gravity. The second clock is on a spaceship orbiting very close to a black hole's event horizon. From our perspective on Earth, we would see the second hand on the spaceship's clock ticking incredibly slow. For every year that passes for us, maybe only a few minutes would pass for the crew on that ship. If that ship were to orbit there for a year according to its own clock and then return it to Earth, its crew would find that decades or even centuries had passed on Earth. They would have traveled into the future, essentially. This isn't just science fiction, it's a real, measurable effect. The GPS satellites orbiting Earth have to constantly adjust their clocks because time for them runs just a tiny fraction of a second faster than it does for us on the surface, where gravity is a little bit stronger. The effect is so minuscule for Earth's gravity, but near a black hole it becomes extreme. As we discussed, for an outside observer watching something fall into a black hole, time for that object seems to slow down until it freezes completely at the end of the event. It's the ultimate form of gravitational time dilation, as if time itself just comes to a stop at the boundary. But again, for the person or object falling in, time feels perfectly normal. What changes is how they're now relative to the now of the distant universe. Once they cross the event horizon, the future for them is only in one direction, towards the singularity. This curvature of space-time is so extreme that the singularity is no longer a place in space, but an inevitable moment in their future, just as next Tuesday is an inevitable moment in ours. This strange behavior of time is one of the reasons black holes are such powerful tools for thought experiments. They push our understanding of reality to its absolute limits, forcing us to accept that time is not the constant, universal river we experience it as, but a flexible, malleable dimension that can be stretched and squeezed by gravity. We've journeyed past the event horizon. We've understood the fate of spaghettification. We've seen time itself bend to the will of gravity. Now we have to confront the ultimate mystery that lies at the heart of the black hole, the singularity. So, what is singularity? According to our current theories, it's a point of zero volume and infinite density. All the mass of the collapsed star, the mass of several suns, is crushed into a region smaller than any subatomic particle. The density, the temperature, and the curvature of space-time all become infinite at this single point. Here, at the singularity, our understanding of the universe just breaks down. The two great pillars of modern physics Einstein theories of general relativity, which describes gravity at the large-scale universe, and quantum mechanics, which describes the strange world of atoms and particles, give contradictory answers. They don't work together to explain what happens at a singularity. General relativity predicts the point of infinite density, but in the real universe, nature tends to avoid infinities. This tells us that our theory is incomplete. We're missing a piece of the puzzle. We need a new theory, a theory of quantum gravity, to truly understand what's happening at the center of a black hole. Some theories speculate that the singularity might not be a point at all, but a quantum fuzz or some other exotic state of matter we just can't describe yet. Others wonder if the singularity might be a gateway to another universe, or a place where new universes are born. This is pure speculation, but it shows how black holes aren't just objects in space, but frontiers of our own knowledge. Around the singularity, we find the accretion disk. This isn't part of the black hole itself, but a structure formed by all this matter that falls into it. Gas, dust, and the shredded remains of stars that wander too close get caught in the black hole's gravitational pull. They don't fall straight in. Instead, they form a vast, flat disk that swirls around the black hole like water swirling down a drain. As the matter in this accretion disk gets closer to the event horizon, it spirals inward at incredible speeds. The friction between the gas particles heats up the disk up to millions of degrees, causing it to glow brilliantly across the entire electromagnetic spectrum, from radio waves to X-rays. In fact, most black holes are discovered not by seeing the black holes itself, but by observing the intense radiation from their hot accretion disks. This glowing, superheated disk is a cosmic warning sign, signaling the presence of the invisible monster at its center. For most of history, black holes were just purely theoretical, just fascinating concepts that came from the mathematics of Einstein's equations. But in recent years, our ability to see the universe has grown so powerful that we've moved from theory to direct observation. One of the most groundbreaking moments in modern astronomy was the first ever image of a black hole released in 2019 by the Event Horizon Telescope collaboration. After years of work, they captured an image of the supermassive black hole at the center of the galaxy, Miser 87, or M87 for short. It was a stunning confirmation of our theories. The image showed a dark central region, the shadow of the event horizon, surrounded by a bright, glowing ring of plasma from the accretion disk. It was exactly as the theory predicted, a silhouette of the black hole against the light of the material swirling around it. A few years later, the same team released an image of Sagittarius A, the supermassive black hole at the center of our own Milky Way galaxy. These images are just profound. They're portraits of gravity itself, and a recent discovery keeps adding new fascinating layers to our understanding. For instance, physicists have discovered the first black hole triple, a system where a black hole is orbited by two different stars. One star is in a very close orbit, while another is incredibly far away. Studying systems like this provides a perfect natural laboratory for testing the limits of general relativity and understanding the intricate gravitational dance between a black hole and its companions. We've also come to understand that supermassive black holes aren't just oddities. They seem to be fundamental parts of galaxies. Nearly every large galaxy, including our own Milky Way, appears to have a supermassive black hole. At its core, these giants can have the mass of millions or even billions of suns. A great debate in cosmology is which came first, the galaxy or the supermassive black holes. Did the black holes form first and act as seeds around which galaxies grew? Or did galaxies form first, with black holes growing over billions of years by feasting on stars and gas at the crowded galactic center? The evidence is still being gathered, but it seems that the evolution of a galaxy and its central black hole are deeply intertwined. They grow together, shaping each other in a cosmic partnership that spans the age of the universe. We've established that nothing can escape from inside a black hole, right? This is true in classical physics, but when we introduce the strange, wonderful rules of quantum mechanics, a loophole appears, a tiny, almost imperceptible one. The brilliant physicist Stephen Hawking proposed that black holes aren't entirely black. They should in fact glow very, very faintly, and in doing so, they should slowly lose mass and evaporate over an immense time scale. This faint glow is called Hawking radiation. The idea behind it is rooted in quantum world, an empty space. Virtual particles are constantly popping into existence. They appear as a particle-antiparticle pair, and they almost immediately annihilate each other, paying back the energy loan that they took from the universe. This happens everywhere all the time. But what happens if a pair of these virtual particles pops into existence right at the edge of a black hole's event horizon? It's possible that one particle falls into the black hole while the other one escapes out into space. From the perspective of a distant observer, it would look as if the black hole just emitted a particle. Because of the laws of conservation of energy, the particle that escaped has to have positive energy to balance the cosmic books. The particle that fell into the black hole must have negative energy. When the black hole absorbs this negative energy particle, its total mass energy decrease by a tiny, tiny amount. So very, very slowly the black hole loses mass. It evaporates. Now, this process is incredibly slow. For a stellar mass black hole, the rate of evaporation is far less than the rate at which it gains mass from background radiation in the universe, so it will continue to grow for now. The time it would take for a black hole the mass of our sun to completely evaporate is unimaginably long, something like 10 to the power of 67 years. That number is so much longer than the current age of the universe that it's almost meaningless to us. But in the far, far distant future of the universe, when all the stars have burned out and all the galaxies have grown dark, these lonely black holes will be the last major objects left, and they too will slowly fade away, one particle at a time, in a final faint glow of Hawking radiation until nothing is left. It is a slow, quiet, and peaceful end for the universe's most violent and extreme objects. Our journey is coming to an end for tonight. We've traveled from a gentle cosmic cloud to the heart of a giant star. We witnessed its explosive death, and we drifted to the edge of the beautiful, mysterious object it left behind. We've seen how a black hole can bend light and stretch time itself. We've explored the point of no return and the deconstruction of spaghettification. We stood at the edge of our own understanding, at the foot of the singularity. The universe is just filled with such wonders, with mysteries that invite our curiosity and our awe. There is so much more to explore, so much more to understand. Thank you for letting me be your guide on this calm, relaxing journey. I hope you feel rested and maybe a little bit more connected to the grand cosmos we are all a part of. If you enjoyed our time together, please consider leaving a like or subscribing for more weekly whispers about the mysteries of our universe. It really helps our small community of nerds grow. And now I have a gentle question for you. Which space mystery should we whisper next? Neutron stars, dark matter, the beginning of the universe itself? Let me know your thoughts in the comments about what you guys thought about this video on black holes, as well as our next video. For now though, it's time to rest. Let the wonders of the cosmos fade into